Okay, leverage point. So it's part of the diagnostic steps we're going to consider when we look at, when we evaluate a model. So let's first define what is a leverage point. Data points that have a large influence on the fitting of the model are called leverage points. So those have a large influence on the fitting, which means it can affect the estimates of the intercept or slope very heavily. So any small change on the data points could change the value of the intercept estimates or slope estimates. And a leverage point is a point whose x value is distinct from the other x values. So that means it should be obvious that one or a couple of points that are further away from like the other group, like a large amount of your data. So two guidelines have large influence on the fitting of the model, and also their x values is far from other x values. And a leverage point can be good or bad when we evaluate, when we do the diagnostic. A bad leverage point is one that is also an outlier. Outliers are those data that do not follow the pattern set by other points. So in other words, they are kind of different from others. The trend for the other data points are not the same as for the location of the outlier. And a good leverage point is a leverage point that is not an outlier. So here, the understanding of outlier is important. You have to know what is an outlier. We will see examples, but the general definition is that they do not follow the pattern set by other data points. And outliers are normally should have like small number. They have small numbers of outlier in data sets. Well, let's see an example of the leverage point. So in this two plots here, I plotted like y bad and y good versus this x. In these two plots, the x values are all the same. The y values are the same except for when x equal to 10. So the y value for this x equal to 10 are totally different for this and that, right? X equal to 10 is a leverage point for both data sets because it's far from other values. See, on both cases, this point are far from this, and this point are far from this. And it has a large effect on the regression line. See, when we have this higher data value for this leverage point, then the line is like this. It's much more horizontal than comparing to this this data set. And I didn't show the estimate of the slope, but the actual numerical value, the slope changed from negative 0.081 to negative 0.958. So it's a big change. So these two are the rule for defining a leverage point. So how do we define if it's a good or a bad leverage point? We would have to determine if they are outliers or not. So in the second set, the y value follows the pattern of others. So this one follows the pattern of this group of data points. So they are on the same line, on the same trend. So they have the same pattern. But for this one, this group of data sets is showing a pattern or a direction in this way, but this data points is over here. It's not really along the trend for this group of data sets. So we consider this one is a good leverage point when it follows the pattern of other data points, but this one does not follow others' pattern. So this is the outlier. So in this first plot, this leverage point is a bad leverage point. Well, we find a numerical rule that can identify xi as a leverage point that is based on the distance if it's away from the rest of x and the extent to which the line is attracted by the given point. And that's the extent, the predicted value of y at xi depends on the actual value of yi. Let's look at this math formula. We can express this second bullet with this following relationship, where you can write this yi hat as a summation of this hij times yj, where j goes from 1 to n. And this hij is defined as this. So it shows you the how like this yi depending for how this predicted value of y, I mean yi hat, depending on the actual value of y's. So it's because this yi hat is a summation of I should say it's a weighted sum of this yj, and this weight is determined by this hij. And we have the proof and derivation for this on the book, which I don't think is necessary that I go through those maths with you. But if you are really interested, you can go to this section 3.2.1 to find the math behind it. Well, let's continue. So for any yi hat, we can actually write it as yi hat equal to this. We basically here we just extract this hii from a group of this hij's when j goes from 1 to n. We just extracted the element I over here, so we can write it as this for the element I and for all the other elements, and where this hii is like this. And this value is commonly called the leverage of the i's data point. So we call this hii being the leverage of i's data point. At the top of the second term address how far that xi is away from the bulk of the x-axis. So like for like most of the data points, and it shows how this yi is related to an effect this yi hat. So that's why it's called this leverage. We know this leverage point would have an impact on the fitted line, and also the leverage point is far from other x values. So in the definition of this leverage, it's definitely should related to like the distance that this value, how far this value is from other axes. Okay, so this is the formal definition by math about a data point's leverage value. Well, the value of hii tells us about the relationship between yi and yi hat. And by looking at this, I should say this example here, it can be shown that if the summation of this hij when j goes from 1 to n, it equals to 1. So if HII is approximately 1, then the other terms should be approximately being 0, because like well, should I go? Yeah. So when we have this one, this HII, okay, I also have this here. So when this HII is 1, then because the summation of all this Hij is equal to 1, if this HII is 1 already, then the rest of for this summation would just be 0. So this value would really close to 0, where this value would just be 1 times yi. So this yi hat should be really close to yi. Well, what does this tell us? So no matter what the other data values are, the predicted value yi will be close to yi, the actual value, when we have HII equal to 1. The leverage points, the leverage of these points only depends on the x values, and Hij is only a function of x and n. So this is just a side note for this leverage of this data points. See, the leverage points only depending on the x values. So, and this Hij, it only involves x and n, but this leverage is it controls, like, no matter what the data, what other data values are, the predicted value should be close to the actual value when this leverage point being 1. Let's actually there is a rule of thumb for us to determine if a point is of high leverage or not. So for simple linear regression, the average HII is 2 by n. A general rule of thumb is that xi is a point of high leverage if this HII is greater than this 2 times the average of HII. Oh, this is a bit of confusing, right? But if you just remember this HII, if it's greater than like 4 over n, then it's considered as a high leverage. So in our good and bad data set earlier, we have n equal to 6. I'm talking about this example. Sorry, I'm talking about this example, and I'm showing you the. I'm going to show you the leverage value for each of these data points. See, this is the label for each data point, and HI, the value of HI, the leverage values for the good and bad data set. These values are the same for both data sets, as both data sets have the same value of x, because yeah, I told you that HII would only involve x and n when you calculate it. But when you're trying to determine if it's a good or I mean, well, if it's a high leverage or not, you just do this. You get this HII, and you do compare it to 4 over n. In which case, it's in this case it's 0.67. So this value is definitely greater than 0.67. So it's of a high leverage. But when we determine it's good or bad, we will have to look at if it's an outlier or not. But for sure, it's already a high leverage point. Yeah, so this is the rule of thumb to determine if a point is of high leverage or not. So now we know how do we determine if a point is a leverage point or not, if it's a high leverage, and we know how to determine if a leverage point is bad or good by looking at if it's an outlier or not. Then how are we going to deal with bad leverage points? There are two main strategies for dealing with these leverage points, and you should really think about the points and what they mean before you choose which strategy you take. So remove invalid data points. That's one of our strategy. That's probably the easy one, but you have to ask the question that, are the data points in question valid? Do they differ in some way from the rest of the data, or are they in some way unusual? If they are just different from the rest of data, or they, well, it could be people just collected by mistake. In that case, you should definitely remove it. And or they have their own meaning, or they belong to your data set, but they really drive your the truth behind your data. So in that case, you may not want to remove it. But if you find the data is not, it does not belong to the data set you are collecting, you should try remove the points and fit the model against without them. A second approach is you fit a different regression model. Because in this case, the data, it does belong to your data set. It's not like wrongly collected. You have to find the right model to fit your data. So if this is the case, you should try adding an extra predictor variables, or you use a more complex model, or just by doing some transformation of Y or X to make the model look better, fit the data better. So these are the two different strategies you can take when you find bad leverage points. Well, so still let's use the same example. So when we have this bad leverage point here, we can change our gear to a quadratic model to fit this data better, right? Apparently this straight line does not fit so well, but when we change it to a quadratic model, it looks good. So this is one way of to deal with this bad leverage points. So in this example situations, good or bad has been very clear. So just by looking at data, looking at the plot, you can determine if it's good, if it's bad. But in practice, that will likely not to be like so clear. There is a large gray area between leverage points that does not follow the pattern and those that do follow the pattern. So it would take a bit of experience to find if there is problem with your data. Also, a note that even good leverage point can influence the model by decreasing the standard error estimates or like increasing the value of R squared. So when you get into the real world, the data will be really messy and complex. You have to like take extra care for them, and in that case, like finding the leverage points are firstly not that easy. Second, even they are good leverage points, like when you're trying to determine if they are good or bad, even if they are good, but still it can make your model look bad. Yeah, so that's the real world analytics.